Hello everyone. So how are you doing? For talk about the meteor spectra in a row, I know, but my talk is gonna be quite short, so don't worry. My topic is the high temperature component in meteor spectra. My name is Vlastimil Vojáček. I'm from the Astronomical Institute of the Czech Academy of Sciences. And as you might know, we can observe two components in meteor spectra. So-called low temperature component that's consists of neutral, mostly neutral atoms and some ionized atoms. And actually, every meteor spectra consists this component. But then you can observe also so-called high temperature component. Its temperature is assumed to be around 10,000 kelvins. It consists of the mostly excited and ionized atoms, and it's assumed that the source of this light is from the meteor shock wave. Compared to the low temperature component, this component keeps the same temperature through all the velocities of the meteors. Is it okay? So low temperature component, well-known lines of sodium, magnesium, iron, and so on. In high temperature components, you can see they are consist of the ionized calcium, ionized magnesium, ionized silicon, and neutral hydrogen. We also assume that part of the high temperature component are the atmosphere lines of atmospheric origin as the oxygen and nitrogen, but they behave a little bit different. So that's why there are these question marks. So especially of the what's can interest us in the high temperature component is the hydrogen line, because as you might heard before, it's a potential tracer to the water and organics in the meteorites. Since this component can be observed only on high speed meteors, and it's actually its contribution can be only up to 5% max of the all light from the meteors. There's not been much studies on this component, but recently very nice work of Matlovic and colleagues. They focused on the hydrogen line, and for the very first time they used like a representative amount of meteors. So that kind of inspired us. For our study, we used spectral cameras of European Fireball Network. Marco talked about it, and you know it, so I can skip this. So about our observations, I was picking up the radiation. I went through our catalog of spectra we have in the time window about 7 years. We collected about 800 spectra, and I was looking on the radiation of each spectrum if there is some radiation between like 600 to 700 nanometers, because that's the region where the silicon and H alpha is. And you can see that I found only 37 spectra with any kind of radiation in that region. So we did our calibrations on these spectra and so on, and I looked, are there what's the source of this radiation, and it's not only silicon or hydrogen, especially the slow ones. You can see the difference. So especially the slower ones didn't contain silicon or hydrogen. Does it work? Yeah. But you could see there was a continuum, and especially bands of oxygen iron. Or there was spectra that look very promising because you could see separated lines, but they were not silicon or hydrogen. They were mostly iron and calcium. So all from these 37 fireballs, only 19 contain silicon, and only in 13 I could identify, yes, there is a hydrogen. So what are our results? Not very much yet. When I was applying the abstract, I had nothing. I had like this. And like 1 week ago, I have half of the results. And on Wednesday night, I finished this preliminary analysis. So what we could see. So as expected, most of the, and compared to the previous work, most of the, all of these meteors were faster than about 30, 40 kilometers per second. Most of them were on Halley orbit. And so why is that? Does it mean that, yeah, it's a high temperature component? So that's why you can't see it in a slow meteors, or is there a higher abundance of hydrogen among Halley orbits? Well, most likely the first scenario, but we can see, okay, so pie chart, so you can see, you can trust me. No Jupiter family member, but it's like a small number statistics. So, yeah. So if we look at the relative intensity of hydrogen and silicon compared to the sodium, you can see this trend that the intensities getting brighter with the velocity. That's expected. It's the high temperature component that is velocity dependent. But you can see there are some let's just say outliers that for given velocity they have a higher amount of hydrogen or silicon. So in this case, you are kind of comparing apples on oranges, because you are comparing the low temperature and high temperature component. So we can look at the relative intensities if we compare only the members of the high temperature component. And you can see that the velocity dependence disappeared, right? And that there are really meteors with higher abundance of hydrogen. And it gets more interesting if you look at the shower membership. So for example, here Perseids, they are like together because I couldn't barely see, or if I could identify hydrogen in their spectra. They were bright in a silicon. On the other hand, Leonids, they showed like a diversity in hydrogen or in silicon. So, and this high abundance of hydrogen, this is only one member of Lyrid that we have in this. So as I said, it's at its very beginning, but for me it's promising. Yeah, you can trust me. So you can trust me. You can see the spectra, like Leonids, like really nice silicon and practically no hydrogen, and this black one, the silicon also is low resolution. The silicon and hydrogen is like comparable. So can see how eager you are for the results. So stay in tune, and yeah, we will continue. And so big thanks to organizers, and well, we're gonna see each other next year, right?